Okay, so today we're going to talk about elastic forces, primarily Hooke's law. Robert Hooke was the scariest scientist in the world. Who's the scariest scientist in the world? Robert Hooke. Robert Hooke. Anyway, the elastic forces, objects can be subject to different kinds of stresses, so we can stretch things. Elongation stretch is by pulling objects in opposite directions simultaneously. Or we can compress objects. Compression stress is when we push inward on an object in two opposite directions simultaneously. And in fact, we can even have a shear stress. A shear stress is when we push unevenly on an object in two directions simultaneously, and we actually get a torque around the center of mass. All of those, there's other stress forces that you deal with if you're beginning to do engineering or building, but those are the primary ones. So, how does an object react to stress? Well, you got to consider a couple of things. Number one, is the stretched object made of something that's elastic or brittle? If it's elastic, it can stretch. If it's brittle, it breaks easily. What's the shape of the stressed object? What are its dimensions? The shape obviously is going to make a factor in terms of how it's stressed. And finally, objects that are very elastic will not permanently deform due to stress. So you can stress them and they go back to their original shape. Things like rubber bands and springs are prime examples of these types of objects. So Hooke's law says that elastic objects obey Hooke's law over a range of stresses, meaning you can stress objects a certain amount, but if you overstress them, they won't go back to their original state. So Hooke's law is, the textbook example is the restoring force exerted by an object F is proportional to the amount that is stretched or compressed X and its spring constant K. Written this way mathematically, F equals Kx. So the amount of force applied is going to equal the amount that it's stressed based on something called the spring constant for a particular spring or stretchable object like a rubber band. And again, the higher the K, the more force required to stress an object. K, the spring constant, is measured in a unit called newtons per meter. So the law applies most directly to and is most useful for springs. Let's take a look at some example problems now, shall we? Okay, here's a spring on a car. A spring with a spring constant of 10 newtons per meter is stretched 0.5 meters. What force is applied to the spring? Well, using Hooke's law, F equals Kx, 10 newtons per meter times 0.5 meters equals 5 newtons. How about this one? A spring with a spring constant of 15 newtons per meter is compressed with a force of 4.5 newtons. How far will the spring be compressed? Springs like bed springs get compressed, or springs on ballpoint pens. So how much will this one be compressed? F equals Kx, 0.3 meters, about 30 centimeters. Finally, here's the final example. A spring is stretched a distance of 0.4 meters with a force of 20 newtons. What is the spring's spring constant? So again, using the formula F equals Kx, we get that the spring constant is 50 newtons per meter. So Hooke's law is a pretty simple law, but it helps explain the behavior of elastic objects like springs when they are subjected to forces. And we'll deal more with springs later in the course when we study energy stored in springs, because springs are have the great ability to store potential energy. That's it, gang. See you in class.